Okay, so let me start by asking this question. Here I define two fields, HU and HT. And the only requirement that I have is that one of them has in the ground state has a vacuum expectation value or a condensate which has only the upper component. The other one has only the lower component. That's the only requirement I have. And so, plus I haven't observed these particles. In the experiments, they just don't exist. At least when they were building this standard model, they just didn't exist. So rather than introducing so many different fields, may I use a single field for both HU and HT? Okay, first of all, I would like to have the same field that plays the role of HU and HT, but then I still have a problem. One of them in the vacuum has only the upper component, the other one only has the lower component. And furthermore, they should still be transforming under SU2, just like the quark doublet. Now, there is a way out. Let's say that H is HT. Let me just take this field. Now, in the ground state, what I would like to have is, let's say, 0, 1, with some coefficient. This is what I would like to have in the ground. Well, this is what HT is. I would like to have 1, 0, sorry. HT in the ground state was, remember, 0, 1. What I would like to have is I would like to obtain 1, 0 in the ground state. Well, this is not so difficult. This is just 0, 1, 1, 0, 0, 1. In fact, let me put a -1 there. Why -1? It will be apparent in a moment. So this can be one choice, let's say. I can have HT vacuum and multiply it with, this is I sigma 2, multiply it with I sigma 2, and in the ground state, the matrix element, the vacuum expectation value will be 1, 0. The only thing left to check is, does this transform just like the quark doublet? Remember, I want to have a field for it. I want to have a HU field. They both transform as a quark or lepton doublet. That is what I want. Now let me look at how does I sigma 2 HT complex conjugate transform. Remember, it's the complex conjugate, not the Dirac conjugate. Well, this will be, remember, HT transforms as e to the power I alpha n tau n HT. So this will, under an SU2 symmetry, it will become I sigma 2 e to the power minus I alpha n tau n conjugate HT star. I'm just taking not Hermitian conjugate, just ordinary complex conjugate. And, well, what are my tau i's? Tau 0, now tau 1 conjugate is 0, 1, 1, 0 conjugate, which is tau 1. Tau 2 conjugate is 0 minus I 0 with 1 over 2 complex conjugate, which is minus tau 2. And tau 3 conjugate is just 1 over 2 tau 3. Now, in fact, this is why I choose sigma 2 here. Why? Because you see these tau n stars, tau 1 and tau 3, tau n, if n is 1 or 3, tau n star is just tau n. But then, if I commute down with sigma 2, sigma 1 and sigma 3 anti-commute with sigma 2. So when I commute those terms with sigma 2, they will acquire a minus sign. And hence this minus I sigma will become, minus I alpha will just become plus I alpha. For tau 2, now tau 2 star is minus tau 2, so for n is equal to 2, again this will become a plus I. But tau 2 commutes with sigma 2. There won't be any additional signs. So this is actually equal to e to the power I alpha n tau n I sigma 2 HD star. Just like it transforms just like HD in exactly the same way. If HD transforms with this matrix, this new field that I define in terms of HD also transforms exactly in the same way. And hence I can actually choose HU as I sigma 2 HD star, which is also sometimes denoted by HC, the charge conjugated doublet. So I don't even need two new Higgs fields as HU and HD. I can choose one of them as my new field. It will contain new particles. The other one will be just a charge conjugated field, defined in this way. This is the definition. So now practically I have everything. So let me write down my standard model Lagrangian. This we had already written down. I'm adding a new field H, so I need to add the corresponding kinetic term, which will be plus H, no, let me write it in this way, del mu H dagger del mu H. This is the kinetic term. I have to subtract the potential term, which I will write as plus 1 over 2 mu squared H dagger H plus minus 1 over 4 lambda, let me write it lambda 4 H dagger H squared. I will come in a moment why I define this as the potential. This line is minus the potential of the Higgs. This is the kinetic energy of the Higgs. This is the potential of the Higgs. And then I need to add these terms. Yes, I need to add these interactions. Let's say I have QL bar, HC, UR. This will give a mass term to the up-type quarks. Now, I have more than one family. In principle, if this is the ith family, I can have the jth family over here. So let me multiply this with the coefficient lambda Uij. This is the most general term that I can write down within considering the particle content I have. That also contains this term. You see, in principle, this can be from one family, and this UR can be from a different family. Of course, that won't be the mass term, but it will also contain my mass terms, diagonal terms. Then I have minus lambda ujd qli h drj. So these are for the down type quarks. Then I have the same terms for neutrinos in the leptonic sector. These are the so-called Yukawa interactions. And this is my standard model Lagrange. I have half an A4. Now the question is, what does this tell us now? Again, now we need to identify the electromagnetic current. What about the masses of the W and the Z boson? And what are the charges? We have hypercharge, not the electric charge. Where is the electric charge here? Those are the things that we need to identify. Let's start with the Higgs potential, where we, let me say, H dagger H is minus 1 over 2 mu squared H dagger H plus 1 over 4 lambda 4 H dagger H squared. You see the mass has the wrong sign. The mass term has a plus sign here, but here it is minus. So if you like, this is, at least if you look at the around the empty state, the Higgs has an imaginary mass, or it's actually a tachyon. But if you go to the ground state, as we will see in a moment, well, the masses are all real. Well, what does this look like, V, as a function of H dagger H? You see, if H dagger H is sufficiently small, this term will be much smaller than this one. Let's say if H dagger H is, I don't know, 10 to the power minus 20. This is the square of that, negligible compared to this one. So close to H dagger H equal to 0, this potential is just goes down. Well, okay, let me write it. Let me just write the square root. So it's an inverted parabola because of this term. And then as H bar H becomes large enough, this term will start to dominate. So this is my potential. This is how my potential looks. And as is obvious, the minimum of the potential is not at 0 Higgs field, but it is somewhere over here. This is what I would call V. Well, how do we find that point? Well, just take the derivative of the V, the potential, with respect to H dagger H, which will be minus mu squared plus lambda 4 over 2 H dagger H. This should be 0. So H dagger H is twice mu squared over lambda to the 4. This is what I will call V squared. Well, what is my Higgs field now? Yeah, okay, so this is the ground state. Well, let me write my Higgs field in this form. In the ground state, it will be 0V. Well, there can be some fluctuation around the V in the radial direction. E to power I alpha I tau I. Now, Higgs field is a doublet of complex fields. So Higgs field actually corresponds to 4 real fields. So H and alpha I are my 4 fields. You see, if I have a single complex field, I can always write it as e to power I alpha x times, let's say, R of x for real fields R and alpha. I'm basically doing the same thing. This is a U1. I'm doing the same thing for SU2. That is the SU2 analog. I have the radial part. I actually chose one direction and wrote the radial part along that direction. And then I just rotate it to wherever my final field is. Those are the angular dependencies. Now, what does this tell me? Well, H dagger H is now 0, V plus H over square root of 2, 0, V plus H over square root of 2. These alpha fields, they basically disappear. This is equal to V plus H over square root of 2 squared. Now, what is my Higgs potential? Minus 1 over 2. Yes, I'm just writing my Higgs potential now. Mu squared V plus H over square root of 2 squared plus 1 over 2 lambda 1 over 4. V plus H over square root of 2 to the power of 4. Now there are terms independent of H, which will be minus 1 over 2 mu squared V squared plus lambda 4 over 4 V to the 4. There will be terms linear in H, which will be minus mu squared over square root of 2 V plus 1 over square root of 2 V cubed lambda 4 H. These are the linear terms. Plus there will be quadratic terms in H, which will be plus minus 1 over 4 mu squared H squared, this is from the first term, plus 6 over 4 lambda 4 V squared H squared over 2, plus terms of the order of H cubed and H to the 4. Okay, so there will be some constant. Now here, I think I have a mistake somewhere. Let me look at this term, the coefficient of H. Well, the coefficient of A, I have this cross term here with 2 over square root of 2. 2 will cancel this 2. I have minus mu squared over square root of 2 times V. And then I have, from here, I will have 4 V cubed. 4 will cancel this 4 here. And H over square root of 2, that is 1 over square root of 2 over here. So that coefficient is V times minus mu squared over, or V over square root of 2, minus mu squared, plus I have lambda 4, V squared. V squared is 2 mu squared over lambda 4. Well, I have a factor 2 missing somewhere. You see, the idea was I'm at the ground state. I'm at the minimum, so the linear term in H basically vanishes. So this term should be 0. So, oh, sorry, this is my mistake. When I take the derivative with respect to H bar H, this term has a 1 over 2. Here I have a minus 1 over 2. So here there is no 2. There is no 2 here. Lambda 4's cancel, so this is 0. The term linear in H is 0. Now the term quadratic in H is plus, let me say, H squared over 4 minus mu squared, this term. Then I have plus 3 lambda 4. V squared is, again, mu squared over lambda 4 plus higher order terms. So lambda 4's again cancel. This is plus mu squared over 2 H squared plus a constant term plus terms cubic or fourth power of H. So you see, I started with having in my potential energy negative sign minus 1 over 2 mu squared H dagger H. But when I expanded my fields around the ground state, H has a mass plus mu squared, mass term plus mu squared over 2. So this new field H has a positive mass, well, has a positive mass squared. Initially here in the potential, here I had a negative mass squared term, but actually when I expanded near the ground state, the mass squared term is positive. That is, I don't have intact ones in around the ground state. And here I have self-interactions of this H field. Furthermore, alpha fields will not appear. You see, if I only had such a scalar theory, you see, if I had a theory that had the Lagrangian equal to this term, and these two terms, which will be describing 4 real scalars, in principle, when I go to the ground state, in the potential term, only one of those real fields appear. So that field only has a mass, it has self-interactions. Other 3 fields are massless. They don't appear in the potential, they don't have a mass term. So effectively their mass term is 0. Those would have been called Goldstone bosons. So we have a symmetric Lagrangian, these terms, only these terms. If I had only those 3 terms, and then this potential basically breaks the symmetry, this SU2 symmetry, and due to that breaking, I have a massive particle and 3 massless particles. Well, why are they massive and massless? Well, let's look at this potential again. Yes, but note that I'm just drawing the potential as a function of the magnitude. If you would try to draw it in all 4-dimensional graph, each axis corresponding to a different field, you will still have, you see, just imagine rotating it around the z-axis. You have a valley at the bottom, this is the potential we have. You would have this is the U1 case, not the doublet case. If we were looking at U1, this would be the potential, just the 2-dimension, the real part, imaginary part of the field. If you like, the center would be the point of symmetry. Around that point, everything will look symmetric. we are near the ground state. But you see, if you try to excite it in the radial direction, there will be energy quantization. So you should get a minimum amount of energy to be able to excite it in the radial direction. That is what we call the mass. But in the angular direction, you can give it as small an energy as you like. Even a very small push, it will start rolling around this valley. So there's no minimum energy that you need to give. But that is what we mean by zero mass. So here in this case, you will get one massive case corresponding to radial excitations, and one massless case corresponding to angular excitations. Basically the same idea applies here. We have one massive field in the angular excitation and three massless fields in the radial excitations. In the angular excitation. This is the radial excitations become massive, the angular ones, they remain massless. Well, it won't appear here though, not in the standard model, because we have all the other terms which will. Okay, so if I only had these three terms, I would have, of course, the covariant derivatives replaced with ordinary derivatives. I would get three massless bosons and one massive bosons after in the ground state. Now let's look at what happened. Let me look at this term in the gauge theory case. What will that term become? Let me calculate this del mu h. If you remember the definition of del mu, this is ordinary derivative minus ig1 y over 2 b mu minus ig2 sigma n over 2 omega mu n, and my Higgs field is e to power I alpha j tau j 0 v plus h over square root of 2. Now, you see, when I write my Higgs field, Higgs doublet in this form, I'm not assuming anything. Everything. This is just a general parametrization of a doublet in SU2. Every doublet of H I can write in that form. But remember, I have a gauge condition. I have a gauge symmetry. I can make a gauge transformation. Well, this just looks like a gauge transformation. So I can apply another gauge transformation, another SU2 gauge transformation, and eliminate that exponent. So that will be my gauge fixing condition. I will choose a gauge in which the Higgs doublet is real, because gauge transformation will just change the complex parameters, and I can fix that will be my gauge fixing condition, if you like. So apply gauge transformation. To eliminate alpha j. I can eliminate them from my theory completely. They don't appear in my Higgs field, in my potential, in the general form. But even if they would, I could just eliminate them by just a gauge transformation. So that will convert this term to del mu minus ig1 y. This is now, I need to use the Higgs, the hypercharge of the Higgs field, whatever that is. Now there's this H field that will describe and track, that will give me, well, del mu acting on my H field will give me the kinetic term of the H field. There will be B mu or omega mu times the H terms. That will give me the interaction of the Higgs field with this B mu and omega mu's, the new H particle. I'm not interested in those terms for the time being. I will look at what it looks like in the ground state. I will just keep the v term. Well, the derivative is practically zero. The derivative of v is just a constant. So I will have minus I, now g1 yh over 2 b mu plus g2 over 2 omega mu 3. I'm just writing the 2 by 2 matrix. Here I have this 2 by 2 matrix. This is also identity in that 2 by 2 space. Then I will have g1 yh over 2 b mu minus g2 over 2 omega mu 3. Then I have g2 over 2 omega mu minus and g2 over 2 omega mu plus. These omega mu minus and omega mu pluses are just, if you remember our general discussion, previous discussion of SU2, these terms. Times 0v plus other terms. And this is minus I g2 over square root of 2 omega mu minus and g1 yh over 2 b mu minus g2 over 2 omega mu 3 times v. Of course, plus it has other terms. Now, what I would like to calculate is del mu h dagger del mu h, which will be just v squared g2 over 2 omega mu minus squared, and then plus v squared omega mu 3 squared. So in my Lagrangian, I have such a term. Well, this just looks like the mass term of a complex vector field with a mass squared is equal to g2 times v squared over 2. Well, this also looks like a mass term, but you see, it's not the mass of b mu or omega mu 3, because if I open that parenthesis, that square, okay, I will get a b mu squared term, I will get an omega mu 3 squared term, but I will also have a mixed term. It tells me that b mu and omega mu, separately, they are not mass eigenstates due to that omega mu times b mu term. But what is a mass eigenstate is this one. This is a mass eigenstate. And there is also the orthogonal component. This is also a mass eigenstate. These two orthogonal fields with mass of z squared is v squared over 4 G1 squared plus G2 squared. And mass of A squared, well, it doesn't appear. So this is 0. So my, from this kinetic energy of the Higgs, if I expand it near the ground state of the Higgs, I get omega squared omega mu plus omega mu minus, and I get plus mz squared over 2. Sorry, so this is over 2 mz squared over 2 z mu plus z mu minus, and plus 0 over 2 a mu squared. No, z mu doesn't have a plus minus. So my theory actually has one massive complex vector field, one real massive complex vector field, and one massless vector field. And what I observe, I'm trying to explain my observations. I have massive omega bosons, Z boson, and massless photon. So if this is my theory, the identification is now kind of obvious. Omega has this mass, Z have this mass. Omega squared, by the way, this is G2 squared, sorry. Well, I don't know V, I don't know V. So I don't really know what the theory, without measuring V, now I know V, but without measuring V, I cannot really say what the masses should be, but basically I can use this definition of the masses. I know the interaction strength G1 and G2. They also give me the decay of these omega particles into two quarks, or the transition of a quark into another quark by omega or Z boson, or in the case of the leptons, I can determine what G1 and G2 are. Well, I can measure their masses, so these equations tell me what the V should be. Furthermore, it predicts omega squared divided by mz squared. This is just G2 squared divided by G1 squared plus G2 squared. You see, this model predicts that the ratio of the masses of omega and Z bosons, the omega and Z, it predicts that the Z boson should be heavier than the omega boson. Furthermore, the ratio is determined by the interaction strengths. So this is a very strong prediction. And it is tested, and of course it satisfies the experiment. This is, at leading order, this is satisfied up to 3 per mil, if I'm not wrong. If you just pick up measurements of G1 and G2, put it over there, pick up the measured values of omega and Z bosons, this equation is satisfied up to 3 per mil. Of course, there are corrections to these masses, quantum mechanical corrections, higher order corrections, which modify this relationship, but the corrections are small. Now let me also look at these interactions. Let me define. You see here, A mu is G2 over square root of G1 squared plus G2 squared B mu plus G1YH. Sorry, this is G1YH squared. Well, I kept the Higgs hypercharge arbitrary for the time being, but I will just set YH equal to 1. Because YH really, we can determine the ratios of the Higgs-Yukawa, Higgs hypercharge to the hypercharge of other particles. And so one of the hypercharges is kind of arbitrary. You can just fix any one of them you like, and the Higgs is fixed to be 1. So So I would rather avoid writing this YH over and over again. With that definition, so you see here I have two numbers, mixing B mu and omega mu, whose squares are 1. So it's just, you can just define them as the cosine and sine of an angle. So G2 over square root of G1 squared plus G2 squared is defined as cosine of theta Weinberg. This is how we define the Weinberg angle. And G1 divided by G1 squared plus G2 squared, this is the sine of theta Weinberg. So the mass of W divided by the mass of Z is equal to cosine of the Weinberg angle. So at least now, okay, what did we achieve up to this point? We wrote down a model, and now we are looking at whether this model matches with our observation. Now we looked at just this term, and that is the term that leads to the masses of the omega and Z bosons, and this model predicts 3 massive particles, omegas and Zs, and 1 massless particle. And the observed masses, you see this omega over mz. Since we don't know V, we can just fix V such that omega is the theory reproduced the mass of the omega, because V is unknown. There is not many places that we can determine V from. But this ratio depends only on the interaction strength, how the weaken U1 interaction strength of the leptons and quarks, if you like. And this relationship need not be satisfied. So whenever you are writing a model, you will have all these many parameters. If you have 5 parameters, you can of course fit 5 observations. That's not a success. So here I have V that is unknown, so I can always choose V such that this equation is satisfied. Predicting being in agreement with the omega mass wouldn't be a surprise. But this one is a surprise because we measure the left-hand side and right-hand side from completely different measurements. If they agree, they don't need to agree. In an arbitrary model, this relation will not be satisfied. But in standard model, this is the relation we have, and it is confirmed with experiments. Now, what are left? Let's look at the charges. We identify the photon. You see, this is A mu. And A mu is cosine theta Weinberg B mu plus sine theta Weinberg omega mu 3. Z mu is minus sine theta Weinberg B mu plus cosine theta Weinberg omega mu 3. My interaction, my Lagrangian is written in terms of B mu and omega mu. So let me write everything in terms of B mu and omega mu. Let me solve for B mu. B mu is equal to cosine theta Weinberg A mu minus sine theta Weinberg Z mu, and omega mu 3 is sine theta Weinberg A mu plus cosine theta Weinberg omega mu 3, Z mu. Now what I will do to identify the charges is, you see, the interaction of quarks and leptons with A mu, they appear from here. Those are the terms where I have the interaction with vector potential through the covariant derivative. Now the covariant derivative, if you remember, is defined as del mu minus I G1 y over 2 B mu minus I G2 sigma n over 2 omega mu n. I just would like to know how A mu interacts with my fields. So I will just pick up the A mu terms proportional to here. This will be, let me keep the del mu, minus I G1 y over 2 cosine theta omega A mu. This is this term coming from this B mu. Then I have minus I G2 sigma 3 over 2. Now here I have omega mu 3. It comes with sine theta omega. A mu. Plus, of course, I have the other terms. And remember, this should be equal to del mu minus I EQ A mu. Plus, of course, I might have other terms. This is my U1 interaction. This is the electric charge. So Q E times Q is equal to, now remember cosine theta Weinberg was G2 over that coefficient. So G1 times cosine theta Weinberg is actually equal to G2 times sine theta Weinberg. So I have, let me just keep G1 times cosine theta Weinberg times y over 2 plus sigma 3 over 2 A mu. Plus other term. Yeah. Okay, this is enough.
Sigma is a matrix, right?
Yes?
Sigma is a matrix.
Sure. Q is also a matrix. You see, because Q, okay, so now let me apply this to multiplet. E times Q acting on up and down, left-handed up and down coils. This should be equal to G1 times cosine theta omega times y plus 1 over 2, 0, 0, y minus 1 over 2, up and down. Well, this is E times 2/3 U minus 1/3 D should be equal to G1 cosine theta Weinberg y plus 1 over 2 U y minus 1 over 2 D. Well, 2/3 E minus 1/3 D. I'm just subtracting the coefficient of UL and DL from both sides. 1/3 E of D should be equal to G1 cosine theta omega. Well, the left-hand side is, no, there's no D. Well, the left-hand side is, this is minus 1/3 of E. The left-hand side is just E. This is G1 cosine theta omega, or G1 G2 divided by G1 squared plus G2 squared. So this is what E is. So which tells me that the Q acting on, or let me go back here. Remember, now we found that E is G1 times cosine theta omega. So Q, there's no A mu here. Q, the charge of any particle is given as y over 2 plus sigma 3 let me write tau 3 here. Well, I know the charges, I know the values of tau 3. The only thing I don't know in this equation is y. In a multiplet, whether it is a singlet, if we are applying this to a singlet, tau 3 is just 0. It doesn't appear in a singlet. If I'm acting it on a doublet, tau 3 is just sigma 3 over 2. Whatever the value is, if I take the trace of both sides within a multiplet, tau 3 is just 0. So this is the hypercharge. So let's see. I have U and dl. What is the hypercharge here? Well, the trace of Q basically means sum the charges. Well, the charge of an up quark is 1/3. Now, up quark is 2/3, down quark is minus 1/3. So if you just sum them up, you get 1/3. This is 2/3. Y of the hypercharge of the doublets, the quark doublets. What about the hypercharge of the leptonic doublets? Let's say U and D, U and E. Trace of Q is equal to -1. So the hypercharge is -2. Right-handed up quarks, trace of Q is 2/3. There's just a single element. So Y of the up-type quarks is 4/3. Down-type quarks, this is -1/3. So the hypercharge of the down-type quarks is -2/3. Right-handed neutrino, trace of Q is equal to 0. So hypercharge is 0. It doesn't interact with B1. It doesn't interact through U1. And finally, you see, right-handed neutrino. Since it's right-handed, it doesn't interact through SU2. Now we see that it doesn't interact through U1. So right-handed neutrino, even if it exists, it doesn't interact with anything. So if there's something that doesn't interact with anything, how do you observe it? And finally, right-handed electron. I'm writing the right-handed electron, but just muon and tau, they're practically the same thing. Trace of Q is -1, the hypercharge is -2. So we have now identified the hypercharges of all our leptons and quarks.
Still didn't address the right-handed neutrino.
Sorry?
We still didn't address the right-handed neutrino. How do we observe it?
We don't.
Then how do we...
Does it exist? That's a different issue.
Yeah.
Now, we will come to that in a moment. Yes, at least we know that we cannot observe the right-handed neutrino through its interactions. I mean, we didn't include the strong interactions here, but it doesn't interact strongly neither. There's only the gravitational interaction. If it exists, it only interacts through gravitational interaction. Okay, so we have identified the electric charge, we have identified the electromagnetic current, we have looked at the masses of the omega and Z bosons and the photon. What about the masses of quarks? Let's look at the masses of the quarks. Well, the masses of the quarks appear from these terms. Now, again, if I just use the expansion of the Higgs field around the ground state and keep only the vacuum expectation value term, this becomes minus lambda I j u times v u l I bar u r j plus u r j bar u l I. Now let me just plus the Hermitian conjugate, and then I have minus lambda I j d v d l I bar d r j. Let me define these matrices mu ij as lambda I j u times v. md ij is lambda I j d times v. They need not be diagonal. Let me define the up quark matrix as u ds. No, sorry. U charm top and down quark matrices as DSP. Then these mass terms of the quarks they just become UL bar M UR minus DL bar M DR. This is MU, this is MD. Now, if M is not diagonal, I cannot identify these as mass terms. I should diagonalize them. But the problem is lambda matrices are kind of arbitrary. I cannot diagonalize them directly. I mean, M is, I cannot diagonalize them by a unitary transformation, but I can diagonalize it because M is not symmetric, nothing. But I can diagonalize them by what's called the biunitary transformation. And I can write mu is, let me write it LU, mu, MC, MT, RU, this LU dagger, and MD, similarly, LD dagger, MD, MS, MB, there's always this so-called biunitary transformation. If you have an arbitrary matrix, you can diagonalize it by this biunitary matrix. Yeah, if I do that, what happens to my mass terms? It becomes UL bar, LU dagger, some diagonal matrix, or UR, minus DL bar, LD dagger, diagonal matrix, MU, MC, MT, or the DR. Now let's go back to my Lagrangian. Let me look at the left-handed fields and the right-handed fields. Okay, I gave them the same name, but who tells me that UL is the left component of the up quark field, and UR is the right component of the right-handed component of the same field. Or who tells me that I should combine UL and UR together to form the four-component spinner? Nothing in my theory tells me that. So in principle, I can consider arbitrary combinations of the left-handed quarks and arbitrary combinations of right-handed quarks, pick the first ones, combine them into a four-component spinner. Nothing in my theory prevents me from doing that. And in fact, that is exactly what I will do. Let me define U prime R or L as U prime L as LU UL, U prime R as RU UR. Well, similarly for the other components, LD DL RD DR. Now, in terms of these fields, my mass term is now minus mu u bar L UR minus MD U bar D U bar, no, D bar R L DR minus M Q is equal to U D S C B T minus MQ QL bar QR plus the Hermitian conjugates, which are QR bar QL. But these are now my mass terms. Now my quarks are massive. What are the mass values? Well, they are V eigenvalues of these mass matrices. What are those eigenvalues? Well, those are matrices given in this form. Now, note that mass matrices are proportional to V. If I were to calculate also the interaction with the Higgs field, remember V always appears with plus h over square root of 2. So all these interactions will be multiplied by 1 minus h over v square root of 2. No, plus. So you see, if I know v, which I can determine by the masses of my omega and z bosons, I know how my quarks interact with the Higgs field. If I know the masses of my quarks, I know the interaction of the Higgs field with all the quarks. I know all the coupling constants, so I can calculate all the cross-sections, probabilities, etc. They're all known. And the coupling of the Higgs with any one of the quark fields is proportional to the mass of that quark field. So top quark interacts the strongest, the bottom the second strongest, the up quark the weakest among the quarks. Now, of course, there is a problem now. You see, I have defined new fields, these primed fields. I have to express everything in terms of these primed fields. Yes, if you go back, to my Lagrangian, well, I have all these kinetic terms, and there are the interactions within these covariant derivatives. I have to express all of them in terms of my new fields. So let's see, let's start. Let's look at the kinetic terms first. Initially, I have UL bar I del slash UL plus CL bar I del slash CL plus TL bar I del slash TL. These are the kinetic terms for the up-type quarks, which I can write as U. Remember, this is how I define U. Left and R, left and right. Of course, plus I have the terms with L replaced with R. I have the same kinetic terms for the right-handed fields. So this is capital U, L, I del slash capital U, L, plus capital U, now this is bar, U, R, bar, I del slash U, R. Now all the kinetic terms of the up-type quarks are in these two terms. Remember, L and U, this is called a biunitary transformation because L and R matrices, they are unitary. So this will be, remember, so UL is LU dagger UL prime, since LU is unitary. So this is LU dagger UL prime I del slash UL prime bar LU. The same thing for the D. UR prime bar LD I del slash LD dagger UR prime. But LU dagger product is identity. LD dagger product is also identity. So at the end of the day, what I have is this is UL prime bar I del slash UL prime plus UR prime bar I del slash UR prime, which basically tells me that although I changed my original definition of the fields, I started with diagonal kinetic terms in my Lagrangian. The kinetic terms appearing here were diagonal in the original basis. When I combine my fields by defining these primed fields, well, the form stays exactly the same. It doesn't change. The kinetic terms are still diagonal. Well, the same thing will happen for the lepton sectors, basically just a copy of the quark sector. So the kinetic terms in terms of new field are identically as what they used to be before. The mass eigen's, these terms are now diagonal. That's why I chose these new bases. The mass terms are diagonal. The kinetic terms appearing in these two lines, they are diagonal. Plus I have the interactions. Now, what kind of interactions I have? Well, let me look at here. Those are where my interactions will come from. Now, let me look at A mu and Z mu terms. A mu is the electromagnetic interaction. Z mu is so-called the neutral current interaction because Z mu doesn't have any charge. So let's see. In the covariant derivative, I have del mu minus I q e A mu. This we had already defined. Then I have, let me call minus q w Z mu. Well, QW is the weak charge of the up, down, the various particles. I don't really care about them. The reason is, the thing that is important for me is these terms do not change the particle type. And the up-type particles have the same QW, down-type particles have the same QW. So what will this be? This will be, let me write this as, this part as d mu, diagonal part, Again, diagonal in the sense that when I write QL bar del mu QL, I will get UL bar UL plus DL bar DL. This is what I will get. I will not get terms like UL bar times DL. Those will not appear here. But if they don't appear, my argument here is basically the same. Nothing is modified, because here I have UL bar UL plus CL bar CL plus TL bar TL. All those three terms will appear when I sum over the family index. But if I get this combination with the same coefficients, I can always write it as a sum of these two terms. If I transform into my new defined prime fields, they are unitary. The transformation is unitary, so it will remain as it is. So again, nothing changes. My Lagrangian looks exactly the same in terms of my newly defined prime fields. Now let's come to the interesting part. This is my del mu. In fact, I think I wrote my del mu before. What I meant by diagonal terms are these terms. Of course, expressed in terms of A mu and Z mu. This will be del mu, the diagonal part. But then I have minus I G2 over square root of 2, 0, omega mu minus omega mu plus 0. So let me look at the kinetic term. I have QL bar I del mu QLI summed over all i's. These are the ones that will have this omega mu part. The right-handed particle don't have this omega mu part. This will contain some terms, minus I G2 over square root of 2, sum over I, UL bar I, DL bar I, 0, omega mu minus, omega mu plus, 0, ULI, DLI, which will be sum over all flavors, all families, as a UL bar I, DL bar I, omega mu minus DLI, omega mu plus ULI. I probably identified the minus and the plus fields in a wrong way. I will keep with this notation. I didn't yet look at what is the charge of omega mu plus or omega mu minus. So this is equal to, of course, there's a gamma mu here. Sum over all I, U, L bar I, omega minus slash dli plus dli bar omega mu plus uli, which I can also write as capital UL omega minus slash capital DL, this is bar, plus capital DL bar omega slash plus capital UL. Now I can go to the complex primed fields. This will become UL bar L U dagger omega prime slash LD. No, this is LU, the other one is LD dagger, plus DL bar LD, these are all prime fields now, omega plus slash LU dagger U prime L. But you see, now I have LU times LD dagger, which is not necessarily the identity matrix. So these interactions are no longer diagonal. You see, before, when I had these SU2 multiplets, UD, CS, TB, in the original multiplets, I only have transitions within the same multiplet. But now, if I identify U prime, D prime, C prime, S prime, T prime, B prime as my new doublets, let's say, yes, I will get diagonal transitions, but I also have off-diagonal ones, because this main product is not identity. Well, how do I identify D prime? You see, D prime, before, this doublet made sense because U and D, they only made transitions between each other. But now, I mean, I have U prime, C prime, T prime on one hand. Then on the other hand, I have D prime, S prime, B prime. They make transitions among, each one makes a transition from one to the other one. So how do I identify the doublets? Well, the convention is the doublets are identified using, for example, U prime. It is most probably, not definitely, but most probably will make a transition to some other down-type particle, and that is what we call D prime. So we define D prime, S prime, and B prime. Not really, sorry. We could have made two different cases. One of them, we could have said that, okay, I identify D prime with the quark that U prime transitions to with the most probable, with the largest probability. That could be one way of combining them. Or we could just order them by their mass. Because you see the mass eigenvalues, when we diagonalize them, by changing a different L and R matrices here, I can just change the order of the diagonal entries. That conventionally, the masses are ordered from the smallest masses, mu, larger is mc, mt is even larger. And here, when we group the smallest masses, they also seem to be the quark that couple the most. It doesn't have to be so. Anyway, this matrix, which is not identity, is what is called the CKM matrix. So let's see what we had done. We wrote this model using our physical intuition, and in fact, this is the most general, minimal model that we can write, consistent with the particles we know and the interactions we know. I mean, we don't have to stick with the minimal, but the minimal seems to work. For example, we could have just assumed two different Higgs fields. But we had seen that we can write one in terms of the other one, and again, this seems to work with just a single Higgs field. Then, this is the most general coupling of my particles with the Higgs field so that it will give masses to my particles. We wrote the most general form, but the most general form didn't really give us the mass eigenstates. For quarks, we moved to the mass eigenstate basis. But then if we change our fields, so we define new fields that have a definite mass, we have to look at what happens to the kinetic terms. You see, we have to diagonalize. The kinetic term has a conventional form. The kinetic term has to have that form. If by changing our fields we spoil the form of the kinetic term, then that would be another problem. But we were lucky that when we went to the mass basis for quarks, the kinetic terms for the quarks also remained as they are. Now, of course, there were interactions. There are those interactions which doesn't change charge, let's say, of the quark. Neutral interactions like electromagnetic interactions and interactions through Z mu. They remain diagonal in these new fields, in terms of new field. New fields do not change. With SU2 interaction, they have the potential of changing the particle type. So this A mu and Z mu fields, okay, they have one part which is the U1 interaction, but they also have the other part which is the SU2 interaction, but those interactions do not change the particle type. Flavor isn't changed by the neutral interaction. Then we had looked at the weak interactions, the interactions of W plus and W minus, and we saw that the weak interactions are no longer family diagonal. Now I will drop the prime. I will always be working with the prime fields. I will drop the prime, so I will just say U, D, C, S, and T, B. Now, weak interactions, the charged current interactions, they make all these transitions possible. All those transitions are possible in interaction by omega plus or minus. Well, the up-type quark has to become a down-type quark if it emits such a positively charged omega from charge conservation. So charge currents, you are forced to change the particle type. Neutral currents, Z mu interaction is still flavor diagonal, meaning that U remains as U, or C remains as C, T remains as T. So we don't get what is called the flavor changing neutral currents. This was one of the things that was supposed to be explained, because we know the particle type changes. We knew before the standard model, even up quark becomes a down quark becomes an up quark. Neutron decay is essentially a down quark becoming an up quark. So we know there are such changes that change the charge. But when the standard model was written, we didn't see any quark type changes that conserved the charge, so-called neutral currents. Now, standard model gave us the explanation. So when you do this treatment, this mechanism is also sometimes called the Jim mechanism. It just they don't appear at tree level. What I mean by but they appear at higher orders. You see, it is possible, for example, an up quark emits an omega plus, becomes a down quark, which then, let's say, emits a photon, remains as a down quark. But then the down quark reabsorbs this omega plus, becomes, let's say, C quark. Or you can go the other way around if you like. So here what happened is a charm quark decayed into an up quark and a photon. This is possible. But yes, it requires two weak interactions, not one. At least when the standard model was written, we didn't have enough accuracy to see such decays. And now we observe these decays, and again, it is consistent with the predictions of the standard model. And okay, so what else? Now there's also the neutrino case. I will not repeat it, but practically you can do exactly the same treatment in the case of the neutrinos. And if you do that, what you will obtain is, if you look at the neutrinos, we have the mass eigenstates, let me call them I. There are these terms. If this is not zero, we will get this term. Again, the interactions will be diagonal. They are neutral, so they don't interact with electromagnetically. They interact through Z. Of course, these are the left-handed components only. And, well, we also have this E bar, gamma mu, L, nu, L, omega mu interactions with a possible so-called P, M, and S matrix. This is the Pontecorvo, I don't remember the other ones. This basically gives the off-diagonal transitions. Now, let me go back to these matrices. You see, here the problem was when we went to the new basis, LU and AD, they are both unitary matrices, but they are not equal. And due to their differences, CKM matrix is not identity. But what happens if, let's say, the D quarks were massless? This MD matrix is 0. But that means I can choose LD matrix whichever way I please. There's no restriction on the form of the D matrix. If I can choose LD in whichever form I please, I could have chosen LD to be equal to LU. And hence this matrix would have been identity. Well, of course, I know that the down type quarks are massive. They're definitely massive. So I cannot do this in the quark sector. But for a long time, we believed that the neutrinos were massless. So let me just copy this, in fact. This U, P, M, and S matrix is defined as L nu times L D dagger. LE dagger, sorry. This is the definition. Well, if neutrinos were massless, I could have chosen L nu to be equal to LE. This would be just the identity matrix. But it turns out that it cannot be the identity matrix. Now, neutrinos are strange because you see here, I have a mass term. This mass term requires that I have a right-handed neutrino. Also, although I cannot observe the right-handed neutrino in any interaction except a gravitational interaction, if I have such a mass term, the so-called Dirac mass, the right-handed neutrino have to be there. But neutrinos are weird, because, not weird, they don't have electric charge. So if I only look at, let's say, the electromagnetic interactions, they can also have such a mass. This is also a mass term. And nu LC, in terms of the two component spinors, is actually I sigma 2 times nu L star. In principle, I can also have such a mass. This is called the Majorana mass. Well, this basically tells me that antineutrinos and neutrinos are the same particle, just like the photon. If you look at the photon, if you would like to define an antiphoton, it's the photon itself. And similarly, neutrinos, they are neutral. So how do you distinguish antineutrinos from neutrinos? Their electric charge is the same, so in principle they can be the same particle. Now the problem with this Majorana mass is that how do you get this from the standard model? You don't get this term from the standard model. The only way for you to get this term from the standard model is from, let's say, from the term. You see, neutrinos come with lepton doublets, within a lepton doublets. From this lepton doublet, I have to extract the upper component, or let me write it this way, HL, H dagger L, this will give me the neutrino, multiply it with LCHC. I can get such a term within the standard model only through such an interaction. When the Higgs field acquires a vacuum expectation value, this term becomes this term. But this term is not renormalizable. You see, count the mass dimension. L has mass dimension 3/2. H has mass dimension 1. So this whole term has a mass dimension 5. Lagrangian should have a mass dimension -4. So I have to divide this by some scale, some massive scale. Well, such theories are not renormalizable. So if you try to make calculations, all the computation turns out to be infinite. So of course, this is from the standard model, the neutrinos can only have a Dirac mass and they cannot have a Majorana mass. Of course, this has to be confirmed by experiment. In experiments, we are still looking for a Majorana mass and a Dirac mass. If in the experiment we can measure a Majorana mass, that will prove that the standard model is not complete. So we have to go to some other theories. And in fact, if you estimate this lambda turns out to be 10 to the power 16 GeV around, using the masses we have. And this is, in fact, a good scale. So there are many things that seem to guide us to something at this so-called good scale, GUT scale, the Grand Unified Theory scale. We don't know if there's anything there, but who knows. And of course, if right-handed neutrinos do not exist, then there's no Dirac mass, and the only mass the neutrino has is the Majorana mass. Now, what do we know experimentally at the moment is that neutrinos have different mass squared terms. Their mass squares are different. That's the only thing we know. So not all of them can be 0. And unfortunately, neutrino oscillations do not tell us whether the mass is a Majorana mass or a Dirac mass. So how do we determine the oscillations?
So how do we know if neutrino is the antiparticle of itself?
We don't know. There is a possibility. We also don't know that it is not. Whether it is the antiparticle of itself or not, we don't know. There's still the possibility that it might be. Well, what happens if the neutrino is the antiparticle of itself? Well, have you heard of neutrinoless, zero neutrino, double beta decay? You know the beta decay, right? So in the beta decay, for example, a neutron becomes a proton, emits an electron, and then antineutrino. We know that there are other nuclei, I don't remember the nuclei now, which transform, emitting 2 electrons and 2 antineutrino. Well, if this is possible, what is actually happening here is the quarks are emitting. If you look at this process, what is happening there is neutron has DDU, proton has DUU, 1D quark becomes a U quark, emits an omega. No, so did I write it right? Yes. Emitting an omega minus. Omega minus later decays into an electron and an antineutrino. So here you can have the nuclei prime emitting 2 omega minuses. So I have 1 omega minus here, another omega minus here. Omega minus decays into an electron and an antineutrino. But if this is possible, then in principle this should also be possible. An omega minus becomes an E minus, emits an antineutrino. Antineutrino becomes a neutrino. They are the same thing. This neutrino collides with the other omega minus and becomes an E minus. So what happened here is, here we have 2 omega minuses decaying into E minus, nu bar, nu bar. Here we have 2 omega minuses decaying into E minus, There's no neutrino. This is a double beta decay in the sense that it emits 2 electrons, just like this one. This is a double beta decay, but without any neutrinos. If this is possible only if the antineutrino and neutrino, they are the same particle. So there are many experiments searching for this neutrinoless double beta decay. So if we can measure that it exists, if we can show that it exists, then we know that electrons should definitely have a Majorana mass, and hence standard model cannot explain that Majorana mass. We cannot obtain a Majorana mass for the neutrinos within the standard model. We have to go beyond the standard model. The Dirac mass, well, some people say that the Dirac mass is also beyond the standard model. I don't like it, because essentially, well, when the standard model was written, we thought that the neutrinos were massless, so we just set one parameter to 0. And now we know that that parameter might be non-zero. If that parameter is non-zero, I don't see any difference of that from saying that, okay, this another parameter, we thought it was 0.2, now we know that it's 0.21. So it's the same thing for me, if you ask me. So this is not new physics, but this, if we can measure it, it will definitely tell us that there is something beyond the standard model. So I think I will stop here. Do you have any questions or anything else you want to ask about the standard model that you had heard but don't know what it is?
I'm surprised that we didn't use that much mathematics. We didn't use very really advanced.
Well, as I said, you already have enough knowledge to construct the standard model. Well, to calculate the predictions of the standard model or to be able to go beyond the standard model is a different issue. So now we can calculate some parameters up to 12 digits. But that is a tedious work. But concepts, we have already covered all the necessary concepts. So if no questions, thank you for showing up.